In the presence of a scalar product, for example, in a Hilbert space, then we can try to represent every element of this space in terms of a preferred basis, and therefore consider a one-to-one correspondence between elements and sum of weighted sum of elements of the basis. This is done in Hilbert spaces. It can be done, and the set that we need to fix is called Hilbert basis. So let's define it. So let's V be a Hilbert space, and let's say that we have a countable subset of V, and this set is called Hilbert basis if so Hilbert basis say for V if there are two conditions to be satisfied. One is that these elements, these EIs, are orthonormal. In other words, the scalar product between the ith element and the jth element is, I use the notation of the delta Kronecker delta, which is 1 if the indices are the same and 0 otherwise. Okay. So they should be orthonormal. 2, if we consider the vector space spanned by these elements, this is a dense subset of V. Okay, let me remind you what is the span. The span is all those elements that can be written as sums, finite sums. So n is an integer, and all alpha i's are real numbers. Okay. So these are finitely many elements with coefficients. Now this is going to be a vector space. Of course, it's vector space. But what we require is that it's dense. So the closure of this set is all of V. Okay, some comments. To have an infinite family of orthonormal vectors, necessarily the dimension of this space, of this vector space, should be infinity. Okay, of course we can start also talking about finite dimensional Hilbert space, but that's a very more basic theory. So to have a Hilbert space, we are talking about infinite dimensional Hilbert spaces. Second, so the element AIs are countable, and of course now if instead of taking in this set real numbers, we take alpha I in Q, then the closure of this set is exactly the same because the closure of Q is R. However, now you will see that if you consider rational coefficients, then the set that you have is countable. All these possible sums are countable. So, which means that necessarily V, necessary to have, for V to have a Hilbert spaces, is necessarily that V contains a dense countable set. Okay, so let me write it as an observation that, so if V has a Hilbert basis, then necessarily V is remind you that having a countable dense set is said to be separable. So separable means a countable dense set. So it's separable, and let me add, and infinite dimensional. Okay. I'm going to now prove a theorem that says that the inverse is true. As soon as the Hilbert space is separable and infinite dimensional, then it admits a Hilbert basis. So theorem, every separable and infinite dimensional Hilbert space has a Hilbert basis. Okay, let's prove it. So we know that the space, the vector space is separable, so we can take, so V separable imply that there exists Xn countable set, and dense in V. So now what we do the following. So we take the first vector. If now the second vector, okay, if it is 0, let's remove it, right? So take another. So if the 0 elements, let's throw them away. So take the first element. This defines a line. Now take the second element. If the second element is on this line, throw it. And then continue until you get another vector that is not in the line. So now these two vectors, they will define a plane. And now take as third vector, a vector that is not in this plane, in this span, right? So every time you add a vector, it's because you're adding one more dimension. So, and we continue this. So what I say is that we can extract a subsequence. Let's call it X sigma n, such that X sigma n is not in the span of the previous ones, the span of X of sigma 1, X of sigma n minus 1. And moreover, when we do it, we consider, so this span here is the same of the span of the first n elements of the first sequence, right? Of this first sequence here. Okay, maybe it's not the same m, but for some n. For some n. So, in other words, but let's pay attention. We are not requiring anymore this to be dense. Actually, very different, right? Because we are removing a lot of these vectors. Okay, but what they span as a finite set is the same set. Okay. So what we have is that if you take the span of the whole sequence, then this is the same span as before, and therefore this is, or at least it contains the initial sequence, and therefore the span, the set is still dense. Is dense in V. Okay. Now what we do, we apply the algorithm of Gram-Schmidt to make this sequence orthonormal. And this is the same as in finite dimensions, because we do it step by step. So then we apply Gram-Schmidt algorithm. So what we do, we define the first one. So the first vector is just the first vector, x sigma I, sigma 1, normalized. Then, by iteration, the nth element is going to be what? The element sigma n, x sigma n, minus the projection of him, where pi n is from V to V, is the orthogonal projection, onto the previous span. So span of x sigma 1 dot 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 x sigma n minus 1. Okay, so we take a vector, we remove the projection on the previous elements in such a way that now this is orthogonal to this span, and then we normalize. So here we write the same. So norm of sigma x sigma n by n x sigma n. Okay, and now this sequence defined is a Hilbert space, is a Hilbert basis. Okay. And the theorem is proved. Okay, therefore, being separable and infinite dimensional is the same of admitting a Hilbert basis. And because of the presence of a Hilbert basis, now we are going to see that all such Hilbert spaces are isomorphic. So in other words, as soon as you are considering separable Hilbert spaces, there is only one up to isomorphism. So corollary. Every two separable infinite dimensional Hilbert spaces are isomorphic. Isomorphic really as Hilbert spaces, in the sense that there is a linear isomorphism that preserves the scalar product. Okay, let's write it in the proof. So proof. Okay, for V and W, separable infinite dimensional Hilbert spaces, we want to prove or we want to construct, or we want a map phi from V to W that is linear, that is a bijection, and preserves the scalar product. Remember that the scalar product is completely determined by the norm, because if by polarization, of course, not every norm is then used by scalar product, but these are Hilbert spaces. So if you preserve the norm, you preserve also the scalar product. Okay. So let's construct this map, but now at this point should be clear what is the map. The map is the only linear map that sends a fixed Hilbert spaces of V1 to a fixed Hilbert spaces of V2, or sorry, V and W. So, okay, let EI and let's call it AI bar Hilbert basis of V and W respectively. Okay, so now we set phi of EI to be EI bar. And we extend it and extend it linearly. So linearly, what does it mean? Now we have a map phi defined on the span of the EIs into the span of the AIs I and N. Okay, now let's not make the mistake of thinking that this is equal to V. This is just dense in V. Okay, likewise, this is dense in W. However, this map, see, since these elements are orthonormal, these are also orthonormal, this map here preserves the scalar product. Or in other words, preserves the norms, is an isometry between this space and this space. Obviously, it's surjective, right? Because every element is taken, every element of the basis. Because remember, every element in here is inside a finite sum of the AIs. So let's write it. Observe that phi is an isometry. Okay, bad. So since in particular phi is uniformly continuous, and the set span of the AIs is dense in V, then phi extends continuously and actually as an isometry, or maybe I should be isometric embedding. I don't know, it's subjective yet. Isometric embedding from so extends, no, let's say it extends to V into W. Now let's also pay attention that I'm using the fact that W is complete, right? Because, so maybe I'll write a little bit more. Indeed, what do we do? We take an element X in V. So there exists Xn in span of the AIs such that xn converge to x, then I can consider phi of xn. Now this map here is this is well defined, and I want to consider the limit of the sequence and define this to be phi of x. Okay. However, this sequence here is I claim that this is a Cauchy sequence. Why? Because xn is Cauchy and phi is an isometry. So phi of xn, maybe I'll write it because w, so w complete, because it's Hilbert, complete, implies that phi of xn converge to something y, for some y in w, and we set phi of x equal to y. Okay, now one should check that this is independent on the sequence, but let's leave this as a calculation for you. I want to observe that this map is now surjective. Okay, maybe right here. One needs to also check that the extension does not depend on the choice of xn. Apart from this, we only need to check that phi, now it's defined on all of v into w, is surjective. Okay, so now take an element w in w, let wn in the span of the basis for w, such that wn converge to w. These elements exist converging to w because this is a dense subset. Okay, so now each of these w is in the span, so it is in the image of phi. Okay, before that, let me also say that since wn converge to w, in particular, wn is Cauchy. It's a very similar argument than before. And so now take Vn in V such that phi of Vn is equal to Wn. Phi isometric embedding implies that Vn is Cauchy. The fact that V is Hilbert or complete implies that Vn converges to V for some V. And finally, by continuity, we need to have that phi of v is equal to w, passing to the limit of this equation here. So what we prove is that w is in the image. W was arbitrary. We finished the proof of the fact that two separable infinite dimensional Hilbert spaces are isomorphic as Hilbert spaces. As in finite dimensions, a basis let us write any element of a Hilbert space in a canonical way using the basis. However, when we have infinite dimensions, then we cannot just write finite sums. We have to consider limits of finite sums, so series. So here's the proposition that I'm going to prove. Suppose we have a Hilbert space and with Hilbert basis En. So this countable is a separable Hilbert space, so it meets up a Hilbert space basis, and we fix one. Then what we are going to prove is that for any element x in the space, x is the limit of the sums from 1 to n, so limit as n goes to infinity of the elements scalar product between x and ei times ei. So as you see, so these are numbers times vectors. So for any n, these are vectors. And what we are going to, what we claim is that this sequence, as function of n, the sequence of points in V converge to x when n goes to infinity. Proof. Okay, let's give a name to those sums. So set xn to be the sum from I from 1 to n of x ei ei. Okay, first thing to that so we claim first thing that x minus xn as a vector, it's orthogonal to ei for all I from 1 up to n, the same n here. Okay? So when to x we remove this sum, then it becomes orthogonal to those vectors that we used to define the series. Okay, now let's prove this. Okay, so maybe let's call it J. So then I put the as an x minus sum from I to of I from I 1 to n of x ei ei, and we take the scalar product with ej. Now, okay, what is this? This is scalar product of x with ej minus. Now we're going to have the scalar product of ei with ej. Now, if I is different than j, then this is 0. This scalar product is 0. But for that I equal to j, which exists because j is between 1 and n, is the same number for which we sum, we get 1, and therefore the scalar product becomes x ej. Therefore, and this is 0. So we checked the claim. Good. Now, since xn is in the span of E1 up to En, because it's defined as a weighted sum of those elements, then we get that x minus xn not only is orthogonal to the vectors, these vectors, but also to their span, and therefore to xn. So it's orthogonal to xn. Okay, let's continue. Then we get that, so the norm of x, the norm square, so x can be written as x minus xn plus xn. And now these vectors are orthogonal, and therefore the square norm by Pythagoras is the sum of the square norms. Okay, so since this is a positive number, then we get that we can take a lower bound with xn square, which is exactly, since the AIs are orthonormal, this sum is exactly x EI square, again, if you want, by Pythagoras. Okay, good. Now, what we understand that this sum, okay, this sum, as n varies, is always bounded, and these are positive numbers, is always bounded by this fixed number, which tells us that this sum is summable. Okay, so we get that the sequence xei, where I runs in the natural number, this is a summable sequence in V. Good. Being summable, what we get is that if we sum the tail of this sequence, sorry, I forgot a square here. So square. So if we sum the squares, the tail of the sequence, this as a sequence in n goes to 0 as n goes to infinity. Good. Right. Now we are ready. So now what we're going to prove, we're going to prove that the sequence of xn is Cauchy. So what we have, that if we take x, we take m, n, and m, and we take the difference between these two vectors, now let's take the norm square. Now this is by definition. Let's say that in here, let's take n less than m. So what we get is this is the sum between m, from m plus 1 to m of x ei, which by orthonormality, this is the sum of x ei square from n plus 1 to m, which is less than the sum up to infinity. So this is, I can write sum for I greater than n, xei, which we said before here, it goes to 0 as n goes to 0. Okay, so what we proved is that xn is a Cauchy sequence. But since V is a Hilbert space, so since V is complete, we get that xn converge to some elements. For now, let's call it y, for some y in V. Okay. Now we want to check that what we need to prove is that this y is equal to the original x. Okay, so let's take now the limit in n of the equation x minus xn ei equal to 0, which is true for as soon as n is greater than I. So take the limit, fix I, take the limit in n, and we get that x minus y ei is equal, scalar product is equal to 0 for all I. Which means that x minus y is orthogonal to the span of ei, I and n. So it's in the orthogonal, and since this element is dense, right, then the space coincide with V orthogonal. So x minus y is in V orthogonal, which is the only element 0. So we prove that x is equal to 0, and that x is equal to y, and therefore the xn converges to x, as we wanted to prove.